In the darkest corners of the universe, there exist entities that defy the boundaries of known physics, black holes. These are regions in space so dense, so gravitationally intense, that not even light can escape their pull. For centuries, they were dismissed as theoretical curiosities, but today the evidence is undeniable. Black holes are as real as the stars that give birth to them, and just as mysterious as the universe itself. For British physicist Brian Cox, black holes are not merely fascinating celestial bodies. They are keys to understanding the most fundamental aspects of reality. According to Cox, they are the only known objects in the universe that demand the unification of the two great pillars of modern physics, Albert Einstein's general theory of relativity and the strange probabilistic world of quantum mechanics. At their intersection lie the deepest questions about space, time, and the very nature of existence. The story of black holes began in the 18th century, when two thinkers, English clergyman John Michel and French mathematician Pierre-Simon Laplace, speculated on the existence of stars so massive that their gravity would prevent light from escaping. Using Newtonian physics, they pondered the concept of escape velocity, the speed required to overcome a celestial body's gravitational pull. Laplace proposed that some objects might be invisible simply due to their magnitude, a poetic intuition remarkably close to what we now know. However, as Cox explains, it wasn't until 1915 that Einstein revolutionized our understanding of the cosmos. His general theory of relativity redefined gravity not as a force, but as the curvature of space-time caused by mass. Soon after, German physicist Karl Schwarzschild found an exact solution to Einstein's equations, describing an object so dense it would create a singularity in space-time. Though barely understood at the time, this marked the birth of the modern black hole concept. Despite the mathematics, many physicists remained skeptical. Cox recalls that even great minds like Steven Weinberg hoped black holes did not truly exist, as they seemed too bizarre. Arthur Eddington, a colleague of Einstein, declared with conviction, "There should be a law of nature to prevent a star from behaving in this absurd way." But reality had other plans. Today, we know black holes not only exist, they are common. Supermassive black holes reside at the centers of most galaxies, including our Milky Way. They are born from the collapse of massive stars, their presence confirmed by direct observations. The orbits of stars near invisible cores, and the historic images captured by the Event Horizon Telescope. As our observational tools have improved, the veil surrounding these entities has begun to lift. Through gravitational wave detectors like LIGO, we've been able to listen to the collisions of black holes, rippling the fabric of space-time itself. These discoveries have not only validated Einstein's predictions, but have also opened new windows into the dark and dynamic architecture of the cosmos. Cox believes that we are only beginning to grasp the role black holes play in shaping galaxies and perhaps in driving cosmic evolution itself. Yet for Cox, the real mystery begins at the black hole's edge, the so-called event horizon. From the perspective of a distant observer, any object nearing this boundary appears to slow down, as if time itself grinds to a halt. This effect, predicted by Einstein, puzzled generations of scientists. It suggested that a collapsing star might freeze at the horizon, never fully crossing into the black hole. Cox is quick to clarify. This is a relative illusion. From the falling object's point of view, time proceeds normally. It crosses the horizon seamlessly, experiencing no strange sensation. This divergence in perception is one of the most compelling demonstrations of relativity. That time flows differently depending on where and how you observe. Cox's fascination with black holes is not simply academic. He sees them as portals to the deepest mysteries of existence. In the 1970s, physicist Stephen Hawking demonstrated that black holes require both relativity and quantum theory to be truly understood. This union, still elusive, points toward a deeper framework, the long-sought quantum theory of gravity. In Cox's view, black holes are more than exotic cosmic remnants. They are conceptual gateways that challenge our most basic assumptions. What is time? Can it end? What does it truly mean to exist beyond the event horizon? Looking into these cosmic abysses, Cox invites us to consider more than equations. He sees a reflection of our own quest to understand reality, a meditative act as much as a scientific one. Perhaps, in the silence of black holes, we won't just find the answers we seek, but also new questions we've yet to ask. At the core of a black hole lies one of the most baffling concepts in all of physics: the singularity. For British physicist Brian Cox, this region is not merely a subject of scientific curiosity. It represents a true boundary of human understanding. Contrary to popular imagination, a singularity is not simply a collapse point of matter in space. Rather, in Cox's words, it is the end of time. According to Einstein's general theory of relativity, when a sufficiently massive star collapses under its own gravity, space-time bends so drastically that it can no longer maintain its usual structure. What was once a spatial coordinate, the center of the collapse, transforms into a temporal one. The singularity, then, is no longer a destination in space, but a moment in time. Everything is drawn toward it, not as if moving across a landscape, but as if rushing toward the final tick of a universal clock. It is where time, as we understand it, ceases to exist. To help us visualize this, Cox refers to Penrose diagrams, tools that map how space and time behave inside a black hole. In these diagrams, the singularity appears not as a dot, but as a line, a boundary in time rather than space. This shift in perspective is counterintuitive. What we imagined as a place turns out to be a final moment. It is like walking into the future and realizing that future simply ends. But the singularity is not the only enigma. The event horizon, the invisible boundary surrounding a black hole, presents an even deeper mystery. Here, we're not dealing with the exotic physics of a collapsed core, but with a region where our current physical laws should still hold. And yet, it is precisely at this threshold that a profound contradiction emerges between our two most successful theories: general relativity and quantum mechanics. Cox explains that when quantum theory is applied near the event horizon, it leads to a groundbreaking prediction made by Stephen Hawking in the 1970s. Black holes are not entirely dark. They emit energy. This radiation, now known as Hawking radiation, implies that over vast periods of time, a black hole can gradually evaporate. What once seemed like an eternal prison becomes, instead, a slow drizzle of particles into the void. From this insight arises the famous information paradox. If a black hole eventually disappears, what becomes of all the information it consumed? In physics, information is not meant to be destroyed. Even if we burn a book, the energy and atoms it once contained still exist. In principle, it's possible to recover what was written. But if a black hole vanishes without a trace, does that information vanish with it? Brian Cox sees this dilemma as one of the most profound ever posed by science. It doesn't concern some unreachable singularity buried deep within. It happens right at the event horizon, where our theories should be most reliable. And yet, those theories are in conflict. Initially, Hawking concluded that information was indeed lost. Black holes, he argued, were cosmic erasers, but other physicists such as Leonard Susskind and Gerard 't Hooft opposed this view, insisting that information must be preserved somehow. The debate raged on for decades, stretching into realms that felt as philosophical as they were scientific. Could the universe forget? The paradox challenges more than just our physical theories. It shakes our assumptions about causality, about memory, about whether reality itself has a coherent structure. While current research leans toward the idea that information is conserved, albeit in ways far more intricate than we can yet decode, the precise mechanism remains elusive. For Cox, this tension is not a failure of science, but an invitation. When two of our most reliable frameworks clash in a setting where both should apply, it's likely that a deeper truth lies beneath. It is as though the universe has embedded a puzzle in plain sight, a cosmic riddle inviting us to think beyond. And that riddle, located not in the depths of space, but at the surface of a black hole, could hold the key to a new physics. A quantum theory of gravity, the elusive unification of space, time, matter, and information, may be hidden at this intersection. What was once just a mysterious boundary may turn out to be a window into the very architecture of reality. This frontier between certainty and paradox may ultimately define how we understand emergence, order, and the fragile coherence of the cosmos itself. To the general public, this may all seem abstract or speculative, but Cox is known for making the unimaginable accessible. He paints a picture that stirs the imagination. Everything that has fallen into a black hole, stars, planets, signals, perhaps even civilizations, might be encoded in the radiation it eventually releases, like a final whisper from the universe, carrying with it all that was, transmuted into the faintest particles. In these dark and silent abysses, where scientific tools falter and logic bends, Brian Cox finds not just a technical challenge, but a profound sense of wonder. Because to study the heart of a black hole is not merely to test equations, it is to stare into the edge of time itself. And perhaps, in that final stillness, we'll learn something extraordinary, that the universe remembers even when it seems to fade into nothingness. At the heart of the cosmic mystery, physicist Brian Cox highlights an unexpected twist in our understanding of the universe. Black holes don't merely challenge known physical laws. They may function as information processors. This connection between gravitational behemoths and quantum computation is not a poetic analogy. It is, rather, a profound clue about the very fabric of reality. For decades, physicists have pursued a theory that unites general relativity with quantum mechanics. Black holes, by their very nature, demand this reconciliation. Yet according to Cox, a revolutionary shift occurred when researchers turned their attention to a seemingly simple question. What happens to the information that enters a black hole, especially once it evaporates as Hawking radiation? This is where quantum computation becomes crucial. One of the most confounding questions in modern physics is how information is stored and preserved in a universe governed by quantum laws. Quantum mechanics imposes strict constraints. Information cannot be copied, the no cloning theorem, and it is highly vulnerable to disruption. Engineers building quantum computers grapple with this problem by using what are known as quantum error correction codes. These codes allow quantum information to be stored redundantly, distributed across many components so that even if part of it is lost or corrupted, the whole can be recovered. Astonishingly, Cox points out, Some of the most advanced black hole theories suggest that nature might be using a similar principle. Modern theoretical work indicates that the information falling into a black hole isn't lost, but rather hidden, possibly encoded on the event horizon itself. This gives rise to an extraordinary idea: holography. In simple terms, it's the concept that everything occurring within a volume of space can be described entirely by the information on its boundary, as if the universe were a giant hologram. This isn't just philosophical speculation. It was mathematically demonstrated in a specific framework by physicist Juan Maldacena, who formulated the AD-SCFT correspondence. Although his model applies to a universe unlike our own, many physicists, including Cox, believe it offers a powerful lens for understanding the deep structure of reality. From this perspective, black holes act as information encoders. Every particle, every star that crosses the event horizon leaves an imprint on its surface, perhaps in the form of quantum patterns. Over time, as the black hole radiates and evaporates, that information, though distorted and dispersed, could theoretically be recovered, like a cosmic message encoded in light, waiting to be deciphered. This raises another intriguing point. If information can be preserved at the edge of a black hole, then perhaps the surface, not the volume, of reality holds the key to understanding everything. This idea has led physicists to propose that the universe itself might be governed by a kind of cosmic memory, just as a hologram contains all the information of a three-dimensional object on a two-dimensional surface. The fabric of reality may be similarly encoded. In this view, nothing is ever truly lost, not in stars, nor minds, nor time. The event horizon becomes not a tomb, but a library, silently archiving every detail of cosmic history. This connection becomes even more fascinating when compared with the methods used by engineers in quantum computing. These researchers design systems to preserve data using structures that, in Cox's words, resonate with the principles embedded in the fabric of space-time. In other words, the way we protect quantum data in a lab seems mysteriously aligned with how the universe might store its own information. This parallel leads to a bold conclusion. Perhaps space and time are not fundamental entities. Maybe they don't exist independently, but rather emerge from something deeper, a network of quantum relationships, an entanglement that gives rise to the geometry we perceive as reality. This line of thought, known as emergent space-time theory, suggests that what we experience as here or now is just a secondary manifestation of a deeper informational substrate. To a general audience, these ideas may sound esoteric, but Cox, as always, explains them with remarkable clarity. Imagine being inside a cosmic simulation, where space, time, even you, are not the core of reality, but the visible effects of a deeper code holding everything together. In this framework, black holes are the universe's ultimate processing units, cosmic servers where information is stored, transformed, and eventually released. Cox readily admits that many of these ideas remain speculative. There is no definitive consensus, and the scientific community is only beginning to grasp the implications. But what matters, he says, is that black holes are forcing us to look beyond familiar concepts like space and time, toward an unseen architecture where information and entanglement may be the building blocks of everything. Einstein once spoke of something deeply hidden in nature. That phrase now rings truer than ever. Thanks to black holes and their strange link to quantum computing, we are beginning to glimpse that hidden structure. And though we've yet to fully decode it, each new theory, each collision in a particle accelerator, each faint glimmer of black hole radiation brings us one step closer. Cox reminds us that the quest isn't just academic. If space and time are not fundamental, then our entire view of reality must change. We would be living not in a physical stage, but in an emergent structure defined by logic, probability, and coherence. In such a world, every moment, every particle interaction, every gravitational ripple becomes an expression of underlying quantum information. We may not know for sure whether the universe is a vast computational entity, but, as Cox puts it, there is something profoundly revealing in the way its most mysterious structures behave as if it were. In that subtle dance between the quantum and the cosmic, we may find the key to understanding what it means to exist at all. Brian Cox has spent much of his career probing the limits of physics, and few concepts captivate him as deeply as the possibility that space and time are not fundamental features of the universe. As quantum mechanics and general relativity intertwine in black hole research, a radical hypothesis has emerged. Space-time may arise from something even more elemental, an invisible network of quantum information. One of the most compelling clues supporting this idea comes from black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that the entropy, a measure of information content, of a black hole does not depend on its volume, as one might expect, but rather on the area of its event horizon. This discovery stunned the scientific community. How could all the information inside a three-dimensional space relate only to its two-dimensional boundary? From this paradox arose the principle of holography, which suggests that all the information defining a region of space can be encoded on its boundary. In other words, the universe might operate like a hologram, where the true reality is inscribed on a surface, and our perception of three dimensions is merely a projection. This notion reframes our entire understanding of physical existence. If the world we interact with is merely a projection of information encoded elsewhere, then our experience of solidity, distance, and even time itself may be illusions born from deeper informational processes. Such a view challenges the philosophical foundation of what it means to be. It implies that consciousness, perception, and reality itself may be far more interconnected with the quantum substrate than previously imagined. Physicist Juan Maldacena provided a mathematical realization of this idea, known as the RAD-S-C-F-T correspondence. It proposes that a universe with certain curvature can be entirely described by a lower dimensional system. Although our universe doesn't perfectly match the conditions of Maldacena's model, Cox and other scientists view it as a powerful insight. What we perceive as space-time may be the result of quantum entanglement among more fundamental components. What's even more surprising, according to Cox, is how this concept aligns with the way quantum error-correcting codes are constructed. Just as information in quantum computing is spread across many qubits to protect it from errors, the universe might be arranged so that its cosmic qubits generate space and time through their internal relationships. All of this leads to a deeply unsettling conclusion. The reality we experience, the here, the now, the distances between things, may be a secondary effect of a deeper structure, a hidden code that organizes the cosmos. Perhaps, as Cox suggests, we are only beginning to glimpse the invisible texture of what is truly real. For Brian Cox, one of the most profound mysteries facing science lies not in the depths of black holes, but in the overwhelming silence of the cosmos. If the universe is home to billions of stars, many with potentially habitable planets, why have we found no trace of other civilizations? This question, first posed by physicist Enrico Fermi in the 20th century, forms the basis of what we now call the Fermi Paradox. From an astronomical standpoint, the conditions for life don't appear unique. Earth orbits a fairly ordinary star, nestled in a typical galaxy, and yet, as far as we can tell, intelligent life has only emerged here. Cox views this absence not as an empty void, but as a message in itself. The universe is silent, and that silence is unsettling. One possible explanation is that intelligent life is far rarer than we assume. The exact combination of conditions required, a stable atmosphere, protective magnetic field, plate tectonics, a moon to stabilize axial tilt, might be so unlikely that Earth is in effect a cosmic anomaly. A darker possibility suggests that while life may indeed arise elsewhere, technological civilizations may self-destruct before they can expand or communicate. This brings us to the concept of von Neumann machines, hypothetical self-replicating probes capable of spreading across the galaxy. If a civilization were to create such a machine and launch it into space, it could multiply and disperse rapidly, yet we see no evidence of their existence. This absence strengthens the idea of a filter, a limit that prevents civilizations from surviving long enough to leave lasting traces. Cox also encourages us to consider another possibility. Perhaps we're not alone, but our detection tools are too primitive, or our understanding of time and consciousness too limited, to recognize other forms of existence. There might be civilizations whose modes of life, communication, or expansion are so alien to us that we're simply missing them, as if we're listening on the wrong frequency. The idea that we might be surrounded by signals we cannot yet interpret, or realities beyond our conceptual reach, invites both caution and wonder. It challenges our scientific humility and demands a broader imagination. If life has found other paths, they may be so foreign that only a revolution in perspective could reveal them. Ultimately, this reflection is not merely astrobiological, it is existential. If we are the only conscious intelligence in the observable universe, then the responsibility we bear is immense: to preserve life, to deepen our understanding of reality, and to act wisely. The real question may not be whether we are alone, but whether we are capable of living up to the weight of a silence that perhaps is watching us in return. For Brian Cox, the silence of the cosmos is not merely absence, it is a warning. The hypothesis known as the Great Filter proposes that there exists a formidable barrier preventing civilizations from achieving lasting interstellar development. Perhaps many fail before ever getting that far, undone by the weight of their own complexity. This filter could lie at various stages. It might be that intelligent life is vanishingly rare, or, more troubling in Cox's view, that the real danger begins only after technological advancement. Humanity, in just a few decades, has amassed unprecedented power. Nuclear weapons, biotechnology, artificial intelligence, yet its ethical maturity has not kept pace. As Cox puts it, progress without wisdom is a recipe for collapse. Such a collapse may not be sudden. It might unfold slowly, ecologically, socially, spiritually. Throughout history, civilizations like Rome or the Maya fell due to internal imbalances. Today, those same patterns may be playing out on a global scale. Cox warns that intelligence without an awareness of interdependence becomes dangerous. Advancement does not guarantee survival. A civilization may develop extraordinary technology and simultaneously undermine the very foundations of its existence. But Cox also leaves room for alternative outcomes. Perhaps there are civilizations that have passed through the filter and chosen not expansion, but silence. Inward-looking, sustainable, disconnected from cosmic noise. Or, even more unsettling, perhaps we have already passed the filter. That does not make us invincible, but radically responsible. If intelligent life is exceedingly rare, then every human decision carries cosmic weight. Our species might be among the very few to have reached this level of awareness. In that case, we are not just another evolutionary accident, but a spark in the dark fabric of time, one that could flicker out or illuminate new paths. To Cox, the true challenge of the future is not technical, but moral. Learning to outlive ourselves means overcoming arrogance, thinking beyond short-term interests, and acting with planetary foresight. Perhaps what truly defines an advanced civilization is not its technology, but its ability to preserve life without destroying it. This redefines what it means to be advanced, not in power or conquest, but in restraint and care. A civilization's legacy may not be measured by how far it travels, but by how wisely it treads, safeguarding the fragile balance that allows life to flourish. And in that quiet test, in a universe that offers no answers, the silence may be waiting for our choice. As this cosmic journey draws to a close, Brian Cox confronts one of the most profound and unsettling questions in science. Why does the universe exist in such a way that it can be observed? This question challenges not only physics, but also edges into philosophy and the nature of consciousness. For centuries, science has treated the universe as an external object, a system to be described with equations, laws, and theories. But Cox suggests that this image is incomplete. At the heart of all scientific observation lies something that cannot be ignored. A conscious observer, us. Without perception, there is no experience. Without mind, there is no sensed universe. What does that imply about the nature of reality? Cox is not claiming that consciousness creates the universe. Rather, he points out that the cosmos appears structured, or at the very least compatible, with the emergence of beings capable of observing it, understanding it, and wondering about it. This coincidence, known as the anthropic principle, has been widely debated. Is it merely a tautology? We can observe the universe only because the conditions allow it? Or does it hint at something deeper? He invites us to consider a bolder possibility, that consciousness is not an anomaly within the universe, but an inevitable expression of its evolution, as if the cosmos, through its vast expansion and increasing complexity, not only gave rise to stars and galaxies, but also to eyes that could behold them, minds to narrate them, and questions to keep them alive. This shift invites a more poetic lens through which to view the cosmos, not as a cold machine, but as a story unfolding, one that includes the emergence of beings capable of wonder. This perspective does not contradict science, it enriches it. Equations may describe the curvature of time or the motion of galaxies, but only consciousness can assign them meaning. In this light, the universe is not merely matter in motion. It becomes story, beauty, mystery, and all of it comes alive when it is observed. For Cox, this marks the culmination of scientific maturity, recognizing that consciousness is not a footnote, but a legitimate part of the cosmic narrative. The universe may not require a purpose, but in us it has found meaning. Perhaps the universe was not made to be observed, but in the moment it came alive in a new way. And that spark, that act of seeing, may be the rarest and most precious occurrence in all of existence. And that concludes our video. If you enjoyed the content as much as we did, don't forget to subscribe so you don't miss a single episode. Leave a comment below. We'd love to hear your feedback and suggestions for future videos. And don't forget to turn on notifications to stay up to date with all our updates. Thanks for being part of our community. See you in the next video.